torque is a very specific kind of moment that occurs about a longitudinal axis. So it's a moment, it's basically like a twisting, if you think about it that way. So if I've got a shaft like this, basically twisting it around the x-axis as I have it shown here. So if this is rigidly attached at the wall here, basically the twist gets bigger and bigger as x increases. So at the wall it's 0, and then way out here at the end, it has some angle that it's twisted through. Okay, so if I take that and I grab just some arbitrary disk that has a thickness dx at some distance x away, okay, and I pull out just a little infinitesimal size thing that's a radial distance rho away from the longitudinal axis. That's what we're looking at up here. Okay, so this thing has a thickness of delta x, okay, and it's at a distance of rho away from the center. Okay, now the equation I have written here is basically this little arc length right here, okay, which is delta phi, which is basically the angle of twist, times rho, which again is that radial distance from the center. Okay, that gives me this distance. It also is the shear strain gamma, which is again that angle away from the undeformed, which would have been just a straight line here, okay, times again that distance delta x. So this arc length is either gamma delta x or rho delta phi, and that's what I have here. Now, rearranging it, getting rid of the delta, shrinking that down to an infinitesimal, I have d phi dx is actually equal to the shear strain over the rho. Okay, which, if we think about what happens here as I move out from the center, okay, that strain would actually be 0 at the center. There would be no strain here. If you kind of think about how this guy goes like this, when I get all the way down here, that arc length actually goes to 0 at the center, and it's at its maximum up here. And that's essentially what this is saying, that the strain is 0 at the edge, and it's at its maximum. And of course we're most concerned with the maximum strain because that's what we're trying to get away from at the distance, the furthest distance away. We're calling that c, which is the radius of the shaft actually. Okay, so taking that equation there, I can set my shear strain to rho c over gamma max. Again, rho is arbitrary radial distance, c is the maximum distance, or the radius of the shaft itself. Okay, so then Hooke's law, which relates shear strain to shear stress, okay, through the g. Well, the g will go away because if I put tau g here and tau max g here, it'll go away. But basically now I've related the shear stress, which is generally what we're more interested in, equal to rho over c times tau max. Okay, so we're going to use this to develop what's called the torsion formula. So we're going to take that shaft and we're going to take its tiny little area right here, okay, and it's going to have a tau associated with it, a shear stress at any radius rho. And again, it's 0 tau, the shear stress is 0 at the center and maximum at the edge, which again we're calling that radius c. Arbitrary radius rho, radius of the shaft is c. Okay, so the torque on that is that distance times the force, so it's going to be the radial distance rho times some df, some infinitesimal force that's acting across that. Well, the definition of shear stress is df dA. So plugging in tau dA for df, I get that the torque is rho tau dA. Okay. Well, integrating both sides, okay, the integral of dt is just t, the integral of rho, and what I've done here is instead of tau, I used the equation I had from the previous slide, which was rho over c times tau max times dA. Okay. Now, a few of these things are constant, okay, relative to the area, and that would be the maximum, the tau max, and the radius c. So I bring those out, and I'm left with the integral of rho dA. Okay, so that equation, rearranging things, solving for tau, I get TC over J, and I'll get to J in just a second. That's called the polar moment of inertia. That's essentially this integral rho squared dA. Okay, or so this would be the maximum. Again, that's at a radius of C at the edge of my shaft. Okay, rho would be if I wanted to calculate tau at some specific distance within there. Okay, now again, J is the polar moment of inertia, and that's that integral there, rho squared dA. Okay, well, what I can do is I can take a small ring, radius rho away, a thickness of d rho, okay, and the area of that infinitesimal ring is the circumference 2 pi rho times the thickness d rho. Manipulating that, pulling out what's constant, basically 2 pi comes out, okay, and I'm left with rho cubed d rho. Well, that's rho to the 4th over 4, so 2 over 4 gives me the 1/2, and then rho goes from 0 to c, so that's where the c to the 4th comes from. So polar moment of inertia for a solid shaft is pi over 2 c to the 4th. For a tube, I would just take the outer minus the inner, as shown there. Now, one more thing when it comes to torque, remember that shear is complementary. So what does that mean? Well, it essentially means that if I take that little infinitesimal, okay, but I've got a shear in this direction, I also have the shear in that direction, again, to balance the couple moment from the opposite shear on the back side of that thing. So when I have a shaft in pure torque, there's also a shear stress that acts axially right down longitudinal axis of the shaft. Okay, so remember that complementary property of shear in that I've got a tau in one direction, it also goes perpendicular in the other direction. Okay, now one of the key times we use this is actually with transmissions, power transmissions. Okay, so the definition of power, many of you may know, is work per unit time. So we're looking at joules per seconds or watts or foot-pounds per seconds, or horsepower. And there's conversions between all these. I'll let you look in your book if you need to do that. But again, by definition, it's the time derivative of work. Okay, so it's dw dt. Well, the work of a torque is just that torque. You know, work is force through a distance. Torque would be torque through a distance, where the distance is a change in angle. So I get t d theta dt. Well, d theta dt is what we call omega, which is angular velocity, which is the time rate of change of the angular position theta. Okay, so my power is the torque times omega, where omega is my angular velocity in radians per second. Okay, now I can also do this in frequency just by multiplying by a factor of 2 pi. Okay, so omega is 2 pi f. So if I'm giving something in hertz, cycles per second, you know, basically there's 2 pi radians in every cycle. So there's the conversion between angular velocity and frequency. Okay, and so a lot of times we're trying to figure out shaft design. Now, just recognize that J and C are strictly due to the geometry based on the radius, because J is, again, pi over 2 c to the 4th. So knowing the torque and the allowable shear stress, I can easily find a radius of a shaft that will work, knowing those two things, and design it accordingly. Okay, so again, with power transmission, the key is to relate torque to that power. And once I get that torque, again, you do a shaft design just like we've done previously.